Okay. Okay, so we were here. We discussed these different types of diffuse radiation and the total amount of solar radiation which is falling on
Sir,
the surface.
you're not sharing.
Oh,
So,
okay.
sir, we cannot see your screen.
Okay, okay, okay. Okay, it's visible now.
Yes.
Yes.
Yes, that's
All
good.
right. So now here we can write the equation of total solar radiation which is falling on a tilted surface, this one. So here we can write the total amount of radiation falling on a tilted surface. It consists of these 1, 2, 3, 5 parts. This is beam radiation falling on a tilted surface. Here T is for tilted. Okay. This one beam radiation. Second is diffuse radiation, which diffuse, that is isotropic, that is coming from the entire sky, uniformly from the entire sky. That is isotropic diffuse radiation falling on that tilted surface. Third one is diffuse but circumsolar, falling on the same tilted surface. This one. Fourth one, diffuse coming from horizon. And the last one is tilted, falling on the tilted surface but reflected from the surrounding, or we can call it ground reflected. So that is the total amount of radiation falling. And now here, this unit of this equation is watts per meter square. Everything is written for square meter. So here is the each term. Beam, diffuse. Diffuse has 3 parts. And the last one is reflected radiation falling on a tilted surface. Now, if we include the area of the solar collector or area of that source of radiation, then we can rewrite this equation in terms of watts. This one is watts per meter square. So if we write it in terms of watt, so then we have to see which. Okay. So we need to introduce areas. So now this radiation is falling on that area of collector. So that's why we shall multiply this IT with area of collector, because this total radiation is falling on that area. Okay, here, this one, the beam part. Normally we know the beam part from measurements for horizontal surface. Okay, normally we are given this radiation falling on a horizontal surface. So then I will write it as IB on a horizontal surface. The effect of tilt we included by defining this factor RB. Right, now this is I tilted of beam radiation, and that is falling on that same collector area. Okay, so this one is written like this: I beam on a horizontal surface multiplied by this radiation tilt factor multiplied by collector area. Okay. Now this one is coming from the entire sky, this radiation. So this one, this I diffused isotropic, that is coming from the entire sky area. But all of it, which is coming from the entire sky, only a portion is falling here, because this part of the sky radiation is not falling on that collector. So here we define a geometric factor, which is called view factor, and that is represented by F. It means how much of this sky is viewed by that collector. That's a geometric parameter. So I will explain it separately. I have a separate slide to explain this thing. We use this factor in radiation calculations. So now this term should be clear how we are writing it. The diffuse radiation coming from isotropic sky multiplied by area of sky, that is area of sky, that is the source of this radiation, but only a part of this is falling on that collector. Only the front side of the collector, because the bottom side is not receiving that radiation, or the back side, only the front side. So here we have to define a factor which is called view factor. So this is view factor from sky to collector. Okay. So if this entire collector is receiving the radiation from the sky, then this view factor will be 1. But if the entire only a part of that sky radiation is intercepted by that area, then this view factor will be less than 1. Okay. So we'll see how to find out this view factor, or how to simplify this term, because there are unknown terms in this equation. For example, area of sky, how to define the area of sky, that is very difficult. So we will modify this equation to a simpler form. Next is solar radiation from the circumsolar. Circumsolar is just like beam radiation. It is around that beam radiation. So it can be treated like a beam radiation, like we can write the similar term for this circumsolar. So that is the radiation per meter square, circumsolar diffuse. It can be treated like beam radiation. We know the exact angle of that radiation. It is falling on that collector area, but this collector is not horizontal, that is tilted. So the effect of tilt by using that factor RB from chapter 1. So circumsolar is also treated like beam radiation. Now the next one, this one, diffuse from horizon. So that is the solar radiation diffuse coming from horizon multiplied by horizon area, this one, in 3D, in 360 degree, that whole horizon area. And again, the horizon here at the back is not falling on that collector, because horizon is coming from the entire 360 degree. Okay, but only the front part, because here this is the solar collector which is absorbing or the solar radiation. From the back there is normally an insulation, so it will not allow the solar radiation to enter. So here again we have to introduce a view factor, horizon to collector. Just like here we had sky to collector, view factor. So here we are defining a view factor from horizon to collector. Okay, and this is the area of horizon from which this solar radiation is coming. Plus, now this is reflected radiation. Now this reflected radiation is coming from the surfaces surrounding that collector. Now in the surrounding of that collector, there could be many different types of surfaces. There could be buildings, there could be road, or there is uh, so anything which is present in the surrounding of that collector that will be reflecting that radiation. All right. So here we have to sum all those reflections coming from all those different surfaces which are present in the surrounding of that collector. So summation of all those individual uh, surfaces, the total radiation I which gets reflected I from ith surface, that is I is the total radiation which is falling on that horizontal surface. And every surface has its own reflectance. So here rho is reflected is representing the reflectance of ith surface. And area of that ith surface, there are whatever surface is present, right? And then the view factor from this ith surface to the collector. This is the reflected part from the surrounding. Okay, now things becomes very messy. Let me remove it all and let me explain it again here. So now this equation is now written by introducing areas, because here everything was watts per meter square. So the total radiation falling on a tilted surface multiplied by solar collector area is equal to the beam part. The beam part falling on a horizontal surface multiplied by the tilt factor, because surface is not horizontal, that is tilted, multiplied by area of the collector. Then this is the diffuse radiation, but this diffuse radiation is coming from the entire sky. So that's why this watts per meter square of diffuse radiation multiplied by sky area. But how much of this sky is viewed by the collector? So that is the view factor. The circumsolar diffuse is just like beam radiation. So it has a defined path or defined angle in this region. So that is treated as beam radiation. Diffuse circumsolar falling on a horizontal surface multiplied by tilt factor and falling the part which is falling on that collector area. Horizon, this horizon radiation in watts per meter square is coming from the entire horizon area. Right now, what is that horizon area? That is very difficult to find out. Similarly, this entire sky area, these are not easy to determine. So we will make these difficult terms into a solvable term later on. And similarly, this horizon, how much of this horizon is viewed by the collector? So here is the view factor for horizon to collector. Now the last term, this is the reflected radiation from the surrounding surfaces, whatever surrounding surface is there. Okay, a concrete surface or a road or a water or whatever surface in the surrounding, it's a sand. So there could be so many different types of surfaces. Everyone is receiving that radiation, and everyone, according to its properties, it will be reflecting in every direction. Only a part of it is reaching on that collector area. So that's why here you see summation of all those different surfaces, the total amount of radiation I which is falling on the ground multiplied by reflectance of all of these surfaces, their individual reflectances, multiplied by areas of those individual surfaces multiplied by view factor from this ith surface to the collector. Okay. Okay, so now this completes that equation. But this equation in its current form, it's very difficult to solve. There are so many strange terms or unknown or very difficult to determine. For example, how to find out this sky area, how to find out this horizon area, and also how to find out the diffuse part coming from horizon, how to find out the diffuse part from circumsolar. Okay, how to find all these individual diffuse radiation. Then this is also very challenging, how to find out these individual reflectances, how many surfaces are there, and their areas, how to find out. So theoretically, this equation is okay, it is explaining what is reaching on that surface, but practically now it's very difficult to calculate all these, or it's a very challenging task. So that's why we need to simplify this equation, this complicated equation 46. Okay, so that's what we will do next. But the overall concept should be clear that what this equation is telling, the total amount of radiation falling on that tilted surface consists of all these parts. And that's what we are trying to find out, the total amount of radiation on that tilted surface, because this is required to size that solar system. Okay. Okay, so now next we shall simplify this equation. So I already explained all these terms. Those are also written here. The meaning of all these terms, which I already explained in the previous slide. Hello, any issue? I cannot hear you. Yes, no speak.
We can hear you, doctor. No issue.
Oh, okay, I thought maybe someone asked some question. Okay. Okay, now we shall simplify this equation 46. It's very difficult to solve. Okay. So for that, now let's see what we will. First of all, let me explain this view factor, which you see here. Okay. So now what is meant by view factor? So for example, this is a surface which is emitting radiation in every direction. Okay. Now you see three different surfaces in its surrounding. Now every surface will intercept different radiation because every surface has its own orientation, which is different from each other, and also with respect to this source, their orientation is different. So if I assume a surface like this one, the same surface, I'm showing it here, and there is another surface which is completely surrounding it. So now whatever radiation is emitted by this one, by this surface one, will be intercepted by surface 2. So in this case, I can say F1 to 2 is 1. But I cannot say the same thing for this one. From this surface 1, okay, let me say this is surface 0 to 3, surface 0 to 2, surface 0 to 1. In each case, this view factor will be less than 1 because this surface can intercept only this part of radiation. This part of radiation is not intercepted by 3. So in each case, I can define a different view factor. So f0 to 3, f0 to 2, similarly f0 to 1. In each case, it will be different. f0 to 2 will be almost 0 because the area of that collector is its surface normal is here. So this portion will not receive any radiation emitted by that surface. Only this thickness of that surface will get some radiation, but the front part will not absorb any radiation. So I can say f0 to 2 is almost 0. But for others, I need to define these view factors. So that's how we define view factor, radiation heat exchange, because between different surfaces, that depends upon the orientation of the surfaces with respect to each other. So for that, we have to define this view factor, which is a geometric ratio or geometric quantity. And it does not depend upon the temperature of the surface, 0 or 3, or 0 or 2, or the properties of the surface, alpha, transmittance, absorptance, or emittance. It is purely a geometric term representing the orientation of the surfaces with respect to each other. Okay, so now there is a complete topic of view factor. In heat transfer books, you will see in radiation chapter, in the chapter of radiation, you will see there is a topic of view factor. And there, the methods of calculating this view factor for different surfaces and their orientation with respect to each other, we can define equations. Okay. But here we will not go into that detail. Here we will just use one of the rules or one of the relations of view factors, which will be helpful for us to solve this problem which we are trying to solve. So what is that correlation which we want here? Oh, sorry. Okay. So as I explained, we can define view factor between any two surfaces. If this is surface 1, this is surface 2. Okay. So F1 to 2 represents the amount of radiation which is leaving 1 and reaching 2. This is called F1 to 2, which is leaving surface 1 and reaching surface 2. That is called view factor from 1 to 2. F2 to 1, we call it the radiation leaving surface 2. Now this is surface 2, for example, the entire sky, and the part of it which is reaching here on surface 1, that is called view factor from 2 to 1. Okay, that is written here. The same we can, this is from the radiation chapter of heat transfer for any two surfaces. Their arbitrary orientation in the space. Okay, so there is a complete derivation of view factor equation and the radiation exchange between such two bodies which are arbitrarily placed in the space. Okay, so there are some more terms, solid angles and this angle between normal and the line connecting two surfaces. So that is a complete topic. So instead of going into that detail, there is one important relation, reciprocity relation of view factors, which we can use here. What this tells, let me clean it. So let's see, this is surface 1, this is surface 2. According to this relation, it says f1 to 2 multiplied by area of 1, area of surface 1, and view factor from surface 1 to 2 will be equal to area of surface 2, this is A2, and view factor from 2 to 1. This is always true between any two surfaces. Like here, this is A1. So here I can write view factor from 1 to 2. This is A2. Multiplied by A1 will be equal to view factor from 2 to 1. This is surface 2. And the part of radiation which is reaching surface 1. Because this part is not reaching surface 1. So F2 to 1 multiplied by A2. This will always be equal. So we shall use this correlation of view factors to solve this situation. Okay. So this is just a brief introduction about view factor, and we shall be using this correlation or kind of law of view factors, and we shall apply it here. Okay. Now let's go back to this equation which we saw. Here is that equation. Now in that equation, we will use that view factor law to make this equation simpler, right? Okay, now first of all, what kind of simplification we can do with this term? Because this is very difficult to find out or calculate or estimate because there are so many surfaces in the surrounding of that solar collector. So it's nearly impossible to find out the reflectances and areas of all those collectors. So what we do here, or as an assumption, we assume around that collector there is one single ground surface. There is one particular horizontal surface, and that particular horizontal surface is emitting radiation or reflecting radiation diffusely. Diffusely means in every direction, constant. In every direction, like this one. There is one particular surface with some average or averaged reflectance. That is called ground reflectance. So instead of summing all those, we will simply write it as there is only one particular ground surface having an average ground reflectance which is about 0.6 to 0.8 is the good assumption for that ground reflectance. Okay. Which can be used. But now what about this term? This is very difficult. Here we see this term is area of that ground surface multiplied by view factor from ground to collector. Similarly here, this one, area of horizon and view factor from horizon to collector. And here again, area of sky and view factor from sky to collector. Now just we saw that equation. So we can apply this equation to these three. Now I can write this A as area of sky multiplied by view factor from sky to collector, and I can write it as area of collector multiplied by view factor from collector to sky. I can use that correlation which we saw here, this one. And use it here. So I can replace this this whole term with this one. Area of sky multiplied by a view factor from sky to collector can be written as area of collector, which is normally known, multiplied by view factor from collector to sky, which is easy to determine. Similarly, this one, area of horizon, which we do not know, multiplied by a view factor from horizon to collector, can be written as area of collector and view factor from collector to horizon. Similarly, this one, area of surface around the collector multiplied by area of that view factor from surface to collector can be written as uh, area of collector multiplied by view factor from collector to surface, ground reflected surface. Okay, so now let's introduce these terms into that equation. So this will make our equation much more simpler or easy to solve, right? So I have discussed all these points. Now we implement these into this main equation of 46, right? So now throughout you will have collector area. Now we have replaced this sky area or horizon area or this ith surface area with collector area. Okay, and this is changed, this is changed, this is changed. Collector to horizon or collector to sky or collector to surface. Now throughout in this equation, now we have one collector area. This will be cancelled with this collector area. So here is that equation. Much simpler than 46. So now it is telling us the total amount of radiation falling on a tilted surface is equal to the beam radiation falling on a horizontal surface multiplied by the radiation tilt factor. This is the diffuse radiation falling on a horizontal surface multiplied by the view factor from collector to sky. This is the circumsolar multiplied by beam radiation tilt factor. This is the horizon diffuse multiplied by view factor from collector to horizon. And this is the ground reflected. So we are assuming around the collector there is only one single material of the ground, and for that ground we shall assume some average reflectance. Okay, this is the total radiation falling on a horizontal surface. Okay, now still this equation we can further simplify it, because still there are these terms circumsolar or horizon, which are not easy to find out. Okay, so now we'll further make this equation more easy or more solvable. So there are many radiation models are available. Mic is on. Okay, so there are many radiation models are developed of different complexity. So all those models, they are different from each other based on how they treat these diffuse radiation terms, right? So there are different types of models which will treat these diffuse terms differently. Some are simple, some are very complicated. So the three models which are available normally, these are these ones: isotropic diffuse radiation model, this one anisotropic diffuse radiation model, HDKR, or there is a model uh, proposed by Eshrey. Okay, so in this course or in this book, mainly this model, the more common or the more simpler one we will use. This is called isotropic diffuse radiation model. Okay. So these are more complicated, and so we'll be using this one. So what is that isotropic diffuse model? This isotropic diffuse model assumes that the diffuse radiation, all the diffuse radiation is only coming from sky dome. So diffuse radiation from horizon or circumsolar, we can simply ignore, and we consider all of them is actually coming from sky. Right. Just a minute. Okay. So this particular model assumes that the diffuse radiation is only coming from sky, isotropic sky. Okay. The horizon and the circumsolar we can simply neglect. Right. So now the total radiation which is falling on that surface of the collector is consisting of beam, isotropic diffuse from the entire sky dome, plus this radiation coming from ground reflected. So we will simply ignore these two, circumsolar and horizon. Okay. So now this will make our model more simpler because now we are only considering these are the major parts. By neglecting these two, this will not make a big error or huge error. So now the total radiation falling on the surface is beam, isotropic diffuse from the entire sky, and the radiation diffusely reflected from the ground. So now this will make our equation more simpler. This was the equation before. Now we are simply neglecting this circumsolar and horizon term. So what is left? The other three terms. Now what is this view factor from collector to sky? This view factor, and collector to ground. So here we have equations available for collector to sky. That depends upon beta. Look, if this beta is 0, this beta means it's a horizontal surface, so this will become 1. So it means if this surface is horizontal, so all the radiation coming from this sky dome will be falling on that. So this is collector to sky. So from collector to sky. So all the radiation leaving the collector is reaching the sky. If this beta is 0, so which is this equation. But if this beta is not 0, so it means only a part of it, only this part will reach the sky. This radiation going in this direction will never reach collector to sky only. Okay. So some part of the radiation emitted by that collector will not be reaching the sky, that is hitting the ground, not the sky, when this beta is higher than 0, for example 30 or 15. So here is that effect. This is collector to sky. Okay, beta is the surface tilt. For collector to ground, collector to ground, here is the view factor. Look now, when this beta is 0, when this collector is horizontal, now all the radiation emitted by that collector will never reach the ground. Okay. So then when you put beta equal to 0, so this will make this term 0. So this will become 0 if the collector tilt is 0, beta is 0. But if there is some beta, so it means this term will not be 0 and this v factor will come into play. Okay, so now we can write this equation, this one. So now here is the modified equation 46. Much simpler, which is much easier to solve. Okay, so that complicated equation now is reduced to this equation 49. So now it's easy to solve. That is, the total amount of radiation falling on a tilted surface is equal to the beam part, diffuse part, and ground reflected part. Diffuse part, we are only considering the total amount of radiation diffuse from the entire sky dome, neglecting circumsolar and horizon. Okay. Okay. So now we shall solve a numerical to calculate this solar radiation falling on its surface, right? Using that isotropic diffuse model. So this model which we have used here to simplify our equation is this one, isotropic diffuse model, which simplified this equation to this form 49, equation 49. So in this course, we shall be using this equation 49 to calculate the total amount of radiation falling on a tilted surface, which is any solar collector. Okay. So let's solve a numerical here. Using isotropic diffuse model, estimate the beam, diffuse, and ground reflected components of solar radiation. So how much is the beam part, how much is the diffuse part, and how much is the ground reflected? Right, so this is IB, IT, and this is I coming from the ground. And the total radiation, total is summation of these two, that will be total on a surface which is sloped at 60 degree, means beta is equal to 60 degree. This is sloped towards the south, means this is south. This beta is given as 60 degree. Facing south means the azimuth angle, surface azimuth is 0. Latitude, so here is the location, so that is phi. For the hour of 9 to 10 a.m., so for this particular hour, 9 to 10 a.m. on February 20, it means declination. This is representing omega. Okay. Here the total radiation falling on a collector surface is given. Measured total radiation on a horizontal surface, this I. With the help of that pyranometer, they measured this radiation. Okay. And the ground reflectance is also given as 0.6 rho g to calculate the ground reflectance, ground reflected part of that radiation. Okay. So now this question will use the equations from the previous chapter, and because previous chapter is linked with this chapter. Because here this total radiation is given, but the how much of this total radiation is beam and how much of it is diffuse, that is not given. That is what we need to calculate. All right. So the equations, the main equations which are used to solve this problem are mentioned here. This is what we need to find out. The total radiation falling on a tilted surface. So for that, we need to know how much of beam part is reaching on that surface, how much is diffuse part. This is the diffuse part, ID. This is the beam part, IB. And out of this total, how much is reflected? This is the reflected part, this one. This portion is representing the reflected part. And the diffuse part, only a part of this diffuse is falling on that collector area. This part is not falling, so that's why we have this view factor, effect of this view factor. So now to solve this equation, we need IB and ID from this I. This I is given. Okay. So using that concept of clearness index, KT, we can find out IB. And if you remember what was KT, KT was defined as I, which is given divided by I naught, extraterrestrial, that is terrestrial. Okay. So first we need to find out I naught. I is given, so that will give us KT. Then we have a separate equation of KT. That will give us how much of this is diffused based on KT. We can use this KT in this equation, which we saw these equations. How much is diffused in this total. So this will give us ID. Okay. So once we know ID, so we can find out IB, beam part. Right. Beam part is I minus ID. So once we know beam part, once we know diffuse part, then we can use it here in this equation. And then we also need to calculate RB. So RB was from chapter 1, cos of theta over cos of theta z. So here those data is given to find out this cos theta equation, which we saw in previous chapter, and cos theta z equation, where we need those phi and del, so we can find out RB, effect of tilt. Then this is easy. I is again given, rho g is given, beta is given, so then we can just put values and find out IT. Okay. So I will solve it in the next class. So I just give you an idea how to solve this question. So you can see the chapter 1 is directly linked to chapter 2. In chapter 1, we just find out I naught or G naught or H naught equation. Now we are using them to find out how much is diffused in a given total radiation, terrestrial radiation. Okay. Okay, so I stop here. So we'll solve it in the next class, this question. Okay. I hope you are here, all of you. Okay, so we shall solve the quiz on Blackboard. Okay. Before solving the quiz in Blackboard, it's better if we join in Teams, right? You will do the quiz in Blackboard, but we will be live in Teams, right? So let me first stop the recording.